All right. Well, hi everybody. Thank you for coming to another week of experimental math. This week I'm going to be talking about flexible schemes for pattern avoiding permutations. So here's an outline of what we're going to be covering today. Since this is the first pattern avoidance talk of the semester, I will start with the basics, so just definitions, what is pattern avoidance. Then we'll talk about how experimental methods have been applied to questions of pattern avoidance before. In particular, we'll look at two experimental methods of counting pattern avoiding permutations. We'll look at enumeration schemes, and we'll look at the insertion coding. And then finally, the main goal of this talk is to present a new expansion of enumeration schemes that can solve anything that traditional enumeration schemes can solve, as well as anything that insertion codings can solve. All right, so we'll start with the intro to pattern avoidance. So here's the definition of pattern containment. If you have a length n permutation, we say that it contains a length k pattern if there exist k elements of that permutation that occur in the same relative order as the pattern. So here's an example. The permutation 2, 4, 5, 1, 3 contains the pattern 1, 3, 2, and that's because if I choose just the underlined elements and take them out, they occur in the same relative order as 1, 3, 2. That is, the smallest one comes first, and then the largest one, and then the middle one. However, 2, 4, 5, 1, 3 does not contain 3, 2, 1, because no matter how you choose three elements of this permutation, you're not going to find three of them that are all in decreasing order. The opposite of pattern containment is pattern avoidance. If some pattern or if some permutation pi fails to contain a pattern sigma, then we say that pi avoids sigma. And so oftentimes, most of the time, we want to talk about sets or permutation classes, which is the set of all permutations of some length n that avoid a pattern sigma, or maybe a set of patterns. And we're going to call that either AV of sigma n or just A of sigma n, depending on how lazy I'm feeling. So here's an example. AV of 1, 2, semicolon 3. That's the set of all length 3 patterns that avoid 1, 2. Well, there's 6 length 3 permutations, but only one of them doesn't have any increasing elements. So that's 3, 2, 1. The main question that people ask about pattern avoidance or pattern containment is, for some fixed pattern sigma, find a formula, a generating function, or a recurrence. In general, just find some polynomial time algorithm that will tell you how many length n patterns or permutations avoid that pattern sigma. So that's the most classical question about permutation patterns. So here's some classical results. In 1915, McMahon showed that the number of patterns that avoid 1, 2, 3, they're counted by the Catalan numbers. Erdős and Sekeresh's famous longest monotone subsequence theorem can be phrased in terms of pattern avoidance. If you have a long enough permutation, then it's got to contain either a length k increasing pattern or a length L decreasing pattern. Then Knuth came along in 1968, and he showed that McMahon's result actually applies not just to 1, 2, 3, but to any length 3 pattern. And actually, this was sort of the result that kicked off the study of permutation patterns. And so after 1968, we started to see a lot more people interested in counting these things. All right, so far what we've talked about, some of the classical results we've talked about, have been people who came up with some pattern. They wanted to know how many permutations avoided it, and so they thought really hard, and they maybe got a little bit lucky, and they came up with an answer. What we want to do is we want to think really hard once, and then get answers for many, many, many different classes of permutations. And so that's the idea of experimental methods, is you come up with a paradigm, and then you have your computer use that paradigm to search through many, many, many possible permutation patterns. And for many of them, your computer will figure out how to count them, instead of having to think really hard for each one. So the first experimental strategy for counting pattern avoiding permutations was enumeration schemes. And these are just one of several automatic enumeration techniques. We'll talk about another one in just a second. They are fully rigorous, so if your enumeration scheme says that there are so many patterns of length n that avoid some pattern sigma, then that's true. That's as certain as if a person had proved it by hand. Some important references for enumeration schemes. Well, Zeilberger initially thought of them in 1998. Vatter expanded them significantly in 2005. And then one that I won't talk about so much, but that was important, was Baxter and Pudwell, who expanded them from classical patterns to vincular patterns, but I'm not really going to talk about that, so don't worry too much about it. Alright, so here's an example of how enumeration schemes work. Don't worry about this definition. I just put it on the slides so that I can say that my slides are complete and rigorous. You should instead think about the example. So what I've added to this example here is I've added this 2-1 subscript, and that's called the downfix. And what the downfix is the downfix is the smallest elements of the permutation. And so what this downfix tells you is that 2 and 1 occur in that order. So in every permutation in this avoidance class, the 2 will come first and then the 1. The other thing that I've added is I've added this vector 1, 0, 2. That's called the gap vector. And it tells you how the elements of the downfix are spaced. So this 1 means that there's 1 element that comes before the 2. The 0 tells you that there's 0 elements between the 2 and the 1. And the 2 tells you that there's 2 elements that come after the 1. So notice that every permutation in this class has to have exactly 5 elements. It has to have the 2 and the 1 as its second and third element. And it also has to avoid 1, 3, 2. And so these happen to be the 3 permutations that fit all of those characteristics. Notice that they both have 2 and 1 as the second and third element. Alright, so that's all that this new notation means. Our goal is going to be to find the number of permutations that avoid 1, 2, 3 and that have any downfix you want. And the way we're going to do that is with recurrence. And actually, this is when I should probably tell you that oftentimes I like to write out permutations in 1-line notation. So like, 5, 3, 1, 4, 2, or whatever permutation. But it's oftentimes easier to think about permutations if you write them with dots instead. And so the way I'm going to express this permutation with dots, actually, maybe I'll just do it over here because that's where everyone's sitting anyway. So the way that I would express a permutation with dots is I would say that, so I have my permutation, which was 5, 3, 1, 4, 2. I would put the first dot, the highest, because of the 5, then a dot below that, then I would have the lowest dot, then I would have the 4, so between the 3 and the 5, and then I would have the 2 over here. So hopefully it's clear how to go between the dots and the 1-line notation. The dots are just easier to visualize. Alright, so the first thing that I'm going to do is I'm going to draw 1 dot at the very bottom. And this dot represents the 1 in my permutation. I'm separating out I'm separating out all the permutations in this avoidance class based on where the 1 occurs. Next, I'm going to do something that's not very interesting yet. I'm now going to separate my permutations based on where the 1 occurs and also where the 2 occurs. So this first sum corresponds to permutations where the 2 comes before the 1, so like that. And then the second one is going to correspond to permutations where the 2 comes after the 1, so like that. So nothing exciting has happened yet. But now something interesting is going to happen. And the interesting thing that's going to happen is I'm going to look at this first case, when the 2 comes before the 1, and I'm going to say that actually, this 1 is totally unnecessary. I can just forget about the 1, I can delete it, I can ignore it. The reason I can ignore it is if this 1 ever was part of a forbidden pattern, in other words, ever was part of a 1, 2, 3 pattern, then there would have to be a 2 and a 3 out here somewhere, and hey look, I would already have a 1, 2, 3 pattern using this 2. So the 1 is not necessary. I can throw out the 1, safe in the knowledge that if this 1 was going to cause a problem, was going to be a part of a forbidden pattern, I'll have a forbidden pattern anyway. I can't, in the second case though, I can't throw out the 1. But what I can do is I can look at the gap vector. So So remember, I have my gap vector G1, G2, G3, where G1 is the number of elements that occur before this dot, G2 is the number that occur between the two dots, and G3 is the number that occur after this dot. Well, if G3 is greater than 0, then I'm guaranteed to have some element out there somewhere. And that's going to cause a problem. That's going to be a 1, 2, 3 pattern. So I can't have G3 greater than 0. On the other hand, if G3 is 0, if I don't have any more elements after that, then I can delete this 2. Because that 2 is never going to be part of a forbidden pattern, I can just forget about it. Alright, so that's the idea behind enumeration schemes. And now, once I use these 2 insights, I get a nice recurrence, and I'm able to count everything really easily. Cool. So that's the idea behind enumeration schemes. The general algorithm is you're going to input some downfix and some pattern. You're going to determine which gap vectors force a forbidden pattern to appear at some point. So in our case, that was when G3 was greater than 0. Then a forbidden pattern is guaranteed to appear. Then you're going to say, okay, well say that I have a gap vector which doesn't have that characteristic, which isn't guaranteed to cause a problem for me. So in our case, that was when G3 was not greater than 0, was equal to 0. In that case, are there elements that I can delete? And in this case, yes, I could delete the 2, so I was happy, and I was able to simplify my downfix. All right. And so because of that, I was able to rewrite my avoidance class using a shorter downfix, which drives my recurrence forward, and I'm happy. All right, so that's all I wanted to say about this, enumeration schemes. Fortunately, so that was sort of a kind of a, it was a nice argument, but for anything more complicated than 1, 2, 3, the argument becomes very tedious, and so you just have your computer do it, and it's all great. All right, so let's talk about insertion encoding next. The insertion encoding is just a different way of constructing a permutation element by element. So just like the enumeration scheme, we're going to build it up one element at a time, starting with the smallest element 1, all the way up to the largest element n. And these are references for the insertion encoding. So here's how the insertion encoding works. We always start up here, and what this diamond means is that eventually, so first of all, this diamond means that I'm allowed to put a new number where this diamond is. So I'm allowed to fill that diamond. And in fact, the diamond requires me to fill it. So eventually, I'm going to have to put a number everywhere I see a diamond. When I put in a number, I have a couple choices. One thing that I can do is I can put the number in the middle of a diamond. So that's what happens in this first line. And so as you can see, I put a 1 in the middle of the diamond, and because it's in the middle, there's more stuff, there's more diamonds on either side of it. We call those active sites, the diamonds. So there's active sites on either side of the 1. I will eventually put more numbers into those active sites. Another thing happens in the next line. I put the 2 on the left of one of those active sites, which means that to the left of the 2, we're done. Nothing more is going to come to the left of the 2, but something will continue to happen to the right of the 2. And then the last thing that I can do is I can fill an active site. So that's what happens to this third line. I fill the active site with this 3. Now, nothing more is going to happen to the right. So it used to be that there was an active site to the right of the 1. Now, the active site to the right of the 1 is gone. Nothing more is going to happen to the right of the 1. And so we just build up the permutation in this way. And so this is how you would build up the permutation 2, 4, 5, 1, 3. And while we're building up the permutation in this way, I'm keeping track of where in each active site I put a new element. So the first time, I put an element into the middle of an active site. And in particular, I put an element into the middle of the first active site. And so I record that as M1. Then the next time I put an element into on the left of the first active site, and so I record that as L1. And so in this way, I can encode my permutation as this string of insertions. And so there's a one-to-one mapping between permutations and strings of insertions. And sort of the insight behind this technique is that sometimes it's actually more useful to look at this string and what properties this string has than it is to just look directly at the permutation. So the deal with the strings is that we're going to consider all of the strings that correspond to permutations in some avoidance class. And this group of strings is going to be called the language. And sometimes this language is regular. And when it is, then there's a fast linear time algorithm to calculate the size of that avoidance class, to calculate, in other words, the number of strings that there are. And when the language is regular, we say that the insertion encoding is also regular. And that's what, sorry?
What is a regular language?
I believe, so if people actually know this, they can correct me. I believe that the regular language is something that you can feed in, you can take a string, feed it element by element into some finite automaton, and that finite automaton will be able to tell you whether that string is in the language or not by the time you finish. And Justin's saying I got that right. It's actually not important for what I'm doing. The only thing that's important for what I'm doing is this characterization down here, which is the permutation class is a regular insertion encoding if and only if it contains finitely many vertical alternations. And let me explain what a vertical alternation is, because that is actually important for what I'm going to do. A vertical alternation is a permutation where I can put some line down here, and then the elements of this permutation will alternate above and below the line. So there's some value such that all of my odd elements are below it and all of my even elements are above it, or vice versa. So that's what a vertical alternation is. And if there's only finitely many of these that avoid some class of permutation patterns, then there's the regular insertion encoding, and vice versa. If there's a regular insertion encoding, there's only finitely many of these. And that's the characterization that I actually use. All right. So far what I've talked about are two techniques of counting these pattern avoidance classes that sort of have existed for a while, have existed for at least 10 years. And so what I want to talk about now is what the original work is. And so the original work is answering a question that was posed by Biers-Ariel, actually in this seminar, as well as in a paper that he wrote, which is, can you build a large, sort of a superset of these two techniques that will solve any problem that either of these techniques individually can solve? And the answer to that question turns out to be these things that we'll call flexible schemes. All right, so here's the goal, which is, I guess, what I just said. And here's the main idea of flexible schemes, which is, what if there are restrictions on, what if there are these gap restrictions that don't make the avoidance class equal to 0, but that do let us rewrite it using a simpler downfix. So over here, we have this gap restriction that if G3 was greater than 0, then we were guaranteed no permutations in our avoidance class. But what if that didn't guarantee no permutations, but it was still useful because it guaranteed that we could delete one of these two elements? That would still be helpful information, but that's helpful information that sort of we don't know how to deal with, or we don't know how to make use of in the framework of traditional enumeration schemes. And so the point of flexible schemes is to be more flexible about the sort of information that we're going to use to count these permutation avoidance classes. All right. So I think that the best way to explain this is by doing an example. And so let me erase this, and then we'll do the example. So we're going to be avoiding 1, 4, 2, 3, and we'll also be avoiding 2, 3, 1, 4. And as it turns out, most of the time when you're able to use enumeration schemes, you're able to use enumeration schemes for like sets of patterns. It's much more rare that they work for avoiding a single pattern. All right, so we're going to be avoiding these two permutations. I'm just going to put them in a set to say that I want to avoid all of them. And then I want to know the number of length n patterns that avoid them. All right, so here's our goal. And we're only going to look at one specific downfix. A, B, 3, 2, 1. And the reason that we're only going to look at this down fix is because, first of all length 3 down fixes other than 3, 2, 1, you already are able to reduce with using just traditional enumeration schemes, so there's no need for this extra machinery. And also, this is plenty complicated enough without trying to worry about any of the other ones. All right, so what I'm going to do is I'm going to consider two cases. I'm going to consider the case when G2, so let me actually write out the down fix first. So here's my down fix. 3, 2, 1. And now I'm going to consider three cases, or two cases. My first case is going to be when G2, so here's G2, is greater than or equal to 1. And then I'll also consider when G2 is 0. So when there's guaranteed to be something in here, when there's guaranteed to be nothing in here. All right. So I claim that if there's guaranteed to be an element in this interval, I can delete this one. And that's what I'm going to prove to you. So and when I say delete it, what I mean is that if this one participated in a forbidden subpattern, so if it participated in either of these patterns, then even once I delete it, one of these patterns will still exist. So deleting the one will never turn a permutation that used to be in this class, or that used to not be in this class, and make it a permutation that is in this class. All right, so let's say that I can't, by way of contradiction, let's say that I can't delete the one. Then the one must participate in one of these two patterns. Otherwise, I can go ahead and delete it. If it participates in this pattern, then my life is very easy. So if there's a 4, 2, 3 that follows it, so if there's like a 4, 2, 3 up here, then I'm good because I can just say, well, either of these two other elements of my down fix could have participated in this pattern, so we're good. Even after I delete the one, that forbidden pattern is still there. All right, but what if the one participates in this pattern, this 2, 3, 1, 4 pattern instead? Well, that's when things start to get a little bit hairy. So there's lots of different places that the 2 in this pattern. So let me start by saying that the 1 has to represent the 1 in this pattern. Because if this one's the smallest element of all the elements in this permutation, so it's definitely the smallest element of the 4 that happen to be used in this pattern. So the question is, where does the 2 come in? And there's a bunch of different options. The 2 could be over here. Maybe the 2 comes before the third smallest element of the actual permutation. Maybe the 2 in this pattern is the third smallest element of the permutation. Maybe it comes between these two. Maybe it's the second smallest element of the permutation. There's lots of different options. We're only going to consider this one option because that is already complicated enough. All right, so let's say that the 2 falls to the right, or to the left rather, of the third smallest element of this permutation. Well, in that case, I know that there's some element, I know there's something in here, so let's just draw in a little dot to represent the fact that I know there's something in this gap. And let's see how I finish this pattern. So I need to have a 4 up here somewhere. So I have 2, and then I have a 3 somewhere, so maybe the 3 occurs over here. So maybe that's the 3. And then I have 1, and I have 4. All right, there's my pattern. So let's say that I delete the 1. My claim is that I still have a forbidden pattern. And sure enough, I do. I have 2, 3, and then I can use either this 3 or this 2 as my 1, and then I have 4. All right, so far so good. Let's say now that this 3 occurs over, and actually, even if the 3 occurs over here, I'll still be good because I still will have a 2, 3, 1, 4 pattern, so I still have a forbidden pattern. So what's really, the only case that's bad for me is if the 3 occurs between this 2 and this 1. So if this is my third element over here. Now I'm in trouble. So now I can look at the element that I know has to exist in this interval somewhere. And I can say, well, that might be, it might be, let's see, what do I want to say? Alright, you know what, this is, the point that I want to make with this example is that this is a very tedious calculation to do by hand. If you really want to see how everything works out, I can direct you to a paper on the archive that does go through this example by hand. It's maybe not worth our time right now. The point is that it does work, and as it turns out, the fact that you know that there is guaranteed to be an element in this interval does in fact get you that you can delete this one. If you weren't guaranteed that there was an element in this interval, you wouldn't be able to delete this one. And in fact, if we don't take into account potential deletions that look like this, then there's nothing we can do. This downfix 321 is irreducible in the paradigm of traditional enumeration schemes. And in fact, you can even prove that no traditional enumeration scheme exists that can count the permutations avoiding these two classes. All right. So the point is that instead of doing this by hand, we want to do this with a computer. And so let's talk about what a scheme is to a computer. A scheme is just a set of replacement rules. So a scheme tells you if you have this downfix, 321, which is the downfix that we had over here, it tells you how to simplify it. And the way that this tells me how to simplify it is it tells me, well, first look to see whether this gap condition is satisfied. And this gap condition 0, 1, 0, 0 is satisfied by every gap vector where every coordinate of that gap vector is larger than the corresponding coordinate of the gap condition. So we look at the first coordinate of the gap vector, we see, oh, it's bigger than 0. Well, everything's bigger than 0, so it definitely satisfies that. We look at the second coordinate of the gap vector, and then if it's bigger than 1, then we're still good. And that corresponds to down here, where we look to see if G2 is at least 1. Then we check the third and fourth coordinates, and there everything's bigger than 0, so it definitely satisfies those two. So if G2 is at least 1, then this 3 tells us that we can delete the third element of the downfix and get a simpler downfix. On the other hand, if that's not true, if we don't satisfy this gap condition, then we move on to the next one. And this is just 0, 0, 0. Everything satisfies 0, 0, 0, because every positive number or every non-negative number is at least 0. So every gap vector will satisfy this condition. So that means that every gap vector that we couldn't reduce earlier, that didn't satisfy this condition, we can delete the 1 from. Or sorry, not the 1. We can delete the first element of the downfix from. So that's how you would explain that to your computer. Here's an example of a scheme that counts the number of permutations to avoid 1, 2, 3. We get the scheme that tells us that when we have a 1, 2 downfix, we have to look to see if G3 is at least 1. If it is, then we get 0. And 0 doesn't mean delete the 0th element, because there is no 0th element. 0 means that there's no possible permutation. So if G3 is greater than or equal to 1, there's no possible permutation. And otherwise, we can delete the second element of the downfix. And that's what we saw earlier. On the other hand, if our downfix is 2, 1, then no matter what the gap vector is, we can always delete the second element of the downfix. All right, so the strategy for your computer is that it's going to compute the sizeless avoidance class by considering all possible length 2 prefixes, and then it's going to reduce with the replacement rules that it finds in this scheme. So the idea behind the Maple package that implements this is 2 procedures. One inputs a set of forbidden subpatterns, so like a set containing 1, 2, 3, for instance, and then it either outputs a scheme or it outputs that it couldn't find the scheme, and then the second procedure inputs the scheme and outputs the first however many you want terms of the enumeration sequence. And you can prove that that algorithm runs in order n to the d plus 2 time, where d is the length of the longest prefix in this scheme. So it runs in polynomial time, which is what we want. All right, so that is what a scheme is to a computer, but we also need to talk about how a computer finds a scheme, because as this example showed, you don't want to be looking for schemes by hand. And so thankfully, there's an easy way for a computer to look for a scheme. So if we so let's say that B is the set of patterns we're trying to avoid. So in this case, B was 1, 4, 2, 3, and 2, 3, 1, 4. If we're trying to avoid these patterns, and we have this down fixed 3, 2, 1, and let's say that we've already considered some gap conditions, what we'd like to say is that these two quantities are equal. So the quantity on the left here, that's the number of permutations with this down fix and with this gap vector G that avoid these two forbidden patterns. And we'd like to say that that's equal to the quantity on the right, which is the same thing after we delete the rth down fix element. So if those two are equal, then we can just delete the rth down fix element and we're good. That drives our recurrence forward. What the theorem says is that we're allowed to do that as long as this equality holds for all g small enough. So if we test it for all g that are below this bound, and that's something that your computer knows how to do, it knows how to exhaust over finite sets of things, then this equality is true for every possible g anywhere in the world. And so that means that your computer can do a finite amount of work and derive this scheme. All right, so let's outline the proof of this. So the way the proof goes, and this, I should say that both this and the next theorem borrow heavily from ideas that Vatter used in similar proofs for sort of similar objects. But anyways, the way that this proof goes is, suppose that it's not true. Suppose that deleting one of these downfix elements actually increases the size of your avoidance class. So in other words, suppose that after you deleted this downfix element, you ended up deleting the one occurrence of a forbidden subpattern, and there's a new permutation that now doesn't contain any forbidden subpatterns. So suppose that's true for a large G that's larger than the bound that we have to exhaust up into. So the only way for that to happen is if there's some permutation that, this is old notation that I should have changed. This means AV pi of BG. All right. So that means there is some pattern, or there is some permutation that's in this which would be in this avoidance class. It has the right downfix, that's the right gap vector, except unfortunately, it contains a forbidden subpattern, and also unfortunately, deleting the rth element of the downfix just gets rid of this forbidden subpattern. Well, in that case, let's remove all of the elements. Let's take that permutation that was a problem. Let's remove all of the elements except for the ones that actually create the problem. So that is to say, remove all of the elements except for the ones that actually participate in that forbidden pattern. And what you're going to end up with is a permutation that's still a problem, because it still has a forbidden pattern that you still can get rid of by deleting the rth downfix element, except now its size is very small. Now its size is smaller than the bound we have to exhaust up until, and so we would have found that there was in fact something in that small set of gap vectors that we had to consider that invalidated the equality. And so we're done. All right, so that's one important theorem that lets us find these schemes automatically. Here's another important theorem. So I claimed to you earlier that this flexible scheme was able to handle any permutation class that traditional schemes could, or any permutation class that the insertion encodings could. Hopefully it's clear how this is just a generalization of traditional enumeration schemes. It's just the same thing as enumeration schemes, except we allow you a little bit more freedom in terms of how you choose your replacement rules. But it's not at all obvious immediately why having a regular insertion encoding implies that you have a flexible scheme. So what this theorem says is that if you do have a regular insertion encoding, then you must also have a flexible scheme. Let's do a quick proof outline of this fact as well. So recall that the regular insertion encoding was the same as having only finitely many vertical alterations, where vertical alternation was this thing over here, where there's some line and all of the even elements of the permutation are above it, and all of the odd elements are below it. All right, so if we have only finitely many, then there must be a largest one. Say that the largest one has length 2k. That means that any gap vector with fewer than k positive entries, any gap vector with more than k positive entries is not going to give any valid permutations, because any permutation would have as a subpermutation some excessively long vertical alternation. So that means that we can choose some downfix and some gap vector, and we can just assume that the gap vector doesn't have very many positive entries. We can assume that the gap vector has only k positive entries. Now, in order for a downfix element not to be deletable, there has to be a permutation which we say witnesses it. And to witness a downfix element, that means that you're a permutation and you would have been in this class. You have the right downfix, you have the right gap vector, except there's some forbidden pattern in you that uses I. And when you delete that I, you no longer contain any forbidden subpatterns. But the thing is that each permutation can only witness finitely many I. In fact, each permutation can only witness AI, where A is the length of the longest permutation in this forbidden set, or the longest pattern in this forbidden set. So each of these can only witness finitely many I, and there's only finitely many possible permutations, because this gap vector only has k positive entries. So we can only sort of witness finitely many downfix elements, but we can make as many downfix elements as we want. We can make the downfix as long as we want, and so there's got to be some element, if we make it long enough, that doesn't get witnessed, and so that we can delete. All right. So here are some empirical results to hopefully convince you that these flexible schemes are a useful quantity. So as you can see here, we considered patterns of length 3, patterns of length 4, patterns of length 5, and then pairs of patterns. So a pair of patterns of length 3, a pair of length 4, and one pattern of length 4 and one pattern of length 5. And what we found is that for the first 4 of these, so length 3, length 4, length 5, and pairs of length 3, the performance of flexible schemes is just the same as the performance of enumeration schemes. You don't get anything extra with flexible schemes. But then, when you look at pairs of patterns of length 4, you do get a decent bit extra with flexible schemes. You get about 30% more, give or take. And then, when you look at a pattern of length 4 and a pattern of length 5, you get a lot more when you use flexible schemes. You get like 50% more permutation classes that you're able to count. And it's difficult to run experiments on longer patterns because just the computational, the amount of computational power that you would need to consider those. But I do believe that if we did run experiments on longer patterns, like maybe 2 patterns of length 5 or a pattern of length 4 and a pattern of length 6, then the advantage of flexible schemes would be even greater. There would be even more patterns that these flexible schemes are now able to count. So hopefully you're convinced that these are an improvement over the previous state of the art. All right, so let me take a few minutes to talk about more. Oh yeah, and so I do want to give one caveat on this slide though, which is that it looks like flexible schemes are great, and they are great, but there are reasons why you might still prefer the traditional enumeration schemes or the insertion encoding. One advantage of the insertion encoding is that it gives you linear time enumeration. And so no matter how complicated your encoding is, you're always going to get to count all of your patterns in linear, or all of your permutations in linear time, whereas flexible schemes only give you polynomial time enumeration, and the exponent on that polynomial could be pretty large. A reason that you might prefer traditional enumeration schemes is that for flexible schemes, sometimes flexible schemes exist, but they just have gap vectors that are so long that we can never find them, or that we don't find them in a reasonable amount of time. But with enumeration scheme, or with traditional enumeration schemes, you can find a priori bounds on how long the gap vectors can be, or how large the elements of the gap vectors can be, and so it's possible to just exhaust over all of them. And so that's an advantage of traditional enumeration schemes. Although, as you can see in this evidence, or as you can see in these results, it looks like that doesn't happen very often, that we would have been able to find it with enumeration schemes, with traditional schemes, but it just takes too long with these new flexible schemes. All right. So, future things that you can work on. One thing are called vincular patterns, or dashed patterns. And so the idea behind a dashed pattern is that some of the elements in my pattern have to occur right next to each other. So for instance, in this, to contain the vincular pattern 1, 2-3, it's like having to contain the pattern, the classical pattern 1, 2, 3, except the 1 and the 2 have to occur right next to each other. And so Baxter and Pudwell generalized traditional enumeration schemes so that they can count patterns, or pattern avoidance classes where the patterns to avoid are of this form. Probably it's possible to do the same thing with flexible schemes. That's what I'm working on right now, actually. You also might consider combining schemes with a different paradigm. So far, everything that we've talked about has been of the form, build up a permutation by adding like first the 1, then the 2, then the 3, and see where everything fits in. But that's not the only sort of automatic pattern permutation counting idea out there. There's another one called the structural, I don't know, it has a bunch of different names. I call it the structural paradigm. And so what this looks like is, let me give you an example. Let's say that we're trying to avoid 1, 3, 2. What this paradigm would say is, let's start by identifying the largest element of this permutation. And then I know that everything that comes to the left of this element has to be larger than everything that comes to the right of it. So let me draw that in. So everything here is larger than everything down here. And both of these individually have to avoid 1, 2, 3. Or 1, 3, 2 rather. And so now all of a sudden we have taken our big avoidance class and written it in terms of permutation, or in terms of the number of permutations that avoid, number of much smaller permutations that avoid 1, 3, 2. And so maybe there's a way to combine these scheme ideas with this structural idea to get something that's even better than both of them. You can also ask about more complicated states. So right now our schemes only keep track of downfix elements. What if they kept track of more information? Is there more information that they could keep track of that would help them count more different kinds of things? All right, so some acknowledgements. I'd like to thank Dr. Z, who introduced me to enumeration schemes in the first place. I'd like to thank Biers-Ariel, who posed this problem and also was kind enough to look at a draft of my paper and make a bunch of helpful suggestions. And I'd also like to acknowledge the Rutgers Office of Advanced Research Computing. All of my experimental results were done on the Amaral cluster. And so each of these symmetry classes takes a day and a half to run. And so if I were doing it on my home computer, it would have taken me about a year and a half to do all of this. And instead, I was able to get all of these results in about a week. So thank you, OARC. All right, questions?
Have you tried more than 3 patterns? More than 2?
I have not. That would be another interesting thing. And actually that might be especially interesting because the more patterns you throw in, usually the easier it is to count them.
Yeah, actually now what you do is avoid A and B. So have you tried something like avoid A or B?
I have not tried that.
Would it be very different?
I am not sure. So that's interesting. So that is not a question that there is very much literature on. And so I'm not sure if that's because no one has asked it before, or if that's because it turns out to have like a simple, or if it turns out to like be, if it turns out to not be an interesting question. I'm not sure why. I would have to think about it. But it definitely, there isn't really literature on that, as far as I know. I have not seen literature on Yeah.
So the reason you don't have further lines, rows in the chart, is it because too computational heavy, or?
Yeah, so even if I was just computing like one single pair of length 4 and length 6 pattern, that would be a pretty enormous computation. And it's not clear how to parallelize it. And so that's why I didn't.
And could you explain what you mean by new again?
Yeah, so new just means that when I try to count these symmetry when I try to count the elements in these permutation classes using either the insertion encoding or the traditional enumeration schemes, I couldn't. And that doesn't necessarily mean that it's impossible, because I gave up if I couldn't count things after a day and a half. But it does mean that it's at least not very efficient to use either of these two techniques, and it's faster to do it with flexible schemes. And maybe it's not possible to do it with either of these techniques, and it is possible to do it with flexible schemes. In general, it's very difficult to say, like, a finite scheme does not exist for this permutation class. There's very few classes that we actually know schemes do not exist for. So usually what happens is you do a bunch of work, and if you don't find a scheme, you say, okay, I bet there's not a scheme.
Do we have, maybe you already said this and I missed it, do we know that schemes exist? Are there any theorems about that?
Yeah, well, so, I mean, we have this one.
Right. Okay.
There aren't very many theorems like that. So here's one theorem for when schemes exist.
Okay.
We also so there's some other families, like anything of the form 1, 2 up through k, we know a scheme exists. There's other things that are sort of similar to that aren't exactly this, but are similar to it that we know that schemes exist. In general, there's not a good a priori way to say that schemes either do or do not exist.
With the flexible schemes, earlier you mentioned in 1913, one of the earliest results was counting the number of avoiding stuff being counted by the Catalan numbers.
Yeah.
With flexible schemes, do we have enough data to make any new conjectures about some sequences like that, or?
I mean, it seems that for all but the simplest permutations, they don't have nice sequences. Or at least they don't have sequences that would have a name outside of being the sequence that counts this permutation class. And so we haven't, so flexible schemes have not given us any new results like this. I suspect that that's because new results like this just don't exist. Although I could be wrong.
So do you think there will be like closed form?
It seems pretty hopeless to try to get a closed form for most of these. So like for instance, there's 56. Don't worry too much about what symmetry classes mean. There's 56 equivalent for some equivalence relation permutation classes that consist of one or of 2 pairs of length 4. Most of them have generating functions. 3 of them are conjectured not to have any generating function at all, or any d-finite generating function at all. And so they certainly don't have formulas. Even the ones that do have generating functions, I don't think have closed form formulas, mostly. And then once you get out to here, I suspect that most of these things don't even have generating functions, or don't have d-finite generating functions.
Wait, how do we know the generating functions?
How do we know the generating functions?
Yeah, do we know what they are?
Well, I mean, if you define the sequences, what you mean for the ones that do have d-finite generating functions?
Yeah.
Oh, they are on Wikipedia, so that's how I know what they are.
Okay.
I don't know how they were originally found.
Okay, gotcha.
I think that they were originally found via sort of ad hoc methods. So someone came up with a clever idea to find the generating function for one permutation class.
I think Dr. Lee also has some packages to find, input a sequence and then you
Yeah,
conjecture
that
the,
is true. So that would also work.
or maybe find some recurrence too. Have you like tried recurrence for those?
Yeah, well, so I have not.
Okay.
I suspect that nice recurrences don't really exist for, at least for the new guys. So like for the ones that do have regular insertion encodings, like they're C finite sequences, so they do have nice recurrences. I suspect that for the vast majority of the ones that aren't that are new with the flexible schemes, they won't have nice recurrences. But I could be wrong.
So for the general problem of deciding if a permutation avoids a pattern, is there a better complexity bound than into a D?
For deciding if you avoid a pattern, I suspect that it's exponential time in general. So the n to the d is only like, that's how you generate the enumeration sequence once you already know that the scheme exists. But a scheme existing is kind of like a special thing. Oh, I'm out of time. All right, if you have questions, I would be glad to answer them in private.